Today's presentation is addressing the challenges in integrity management of FPSOs by Biju George of Ocean Engineering. Biju is an experienced marine and oil and gas professional with 3 decades of experience working as a marine engineer with a combined sea service of 80 months on board ocean-going ships, a technical superintendent, a classification society engineer, and a senior integrity engineer with extensive expertise in design approval, technical and integrity management of ships and offshore assets. Biju has received a number of performance awards, one from Azure Energy in November 2023, in recognition of his leadership demonstrated in enabling multiple activities on FPSOs that reduce risk and enable continued operations. He's also a winner of the Core Value Coin Award from Oceaneering in June 2023. He's also received an Exceptional Performance Award from VP in Oceaneering in 2020 and 2019. He has been involved with the Institute of Marine Engineering, Science and Technology, FIMarEST, as CEO Future Coordinator since 2010 and presently serves as the Honorary Secretary of the FIMarEST South East England and London Home Counties. He's a professional review assessor for the Engineering Council and the FIMarEST. Biju holds a bachelor's degree in mechanical engineering from Mahatma Gandhi University in India, a master's degree in marine engineering from Newcastle University, and a doctoral degree in computing and engineering from the University of West London. He's a chartered engineer and a chartered marine engineer, as well as a fellow of FIMarEST. So Biju will give his presentation and then we will respond to any questions at the end here in the audience and online. So those of you online, if you want to put your questions into the chat box, then that would be great. So without further ado, Biju.
Thank you.
Let's go.
Thanks, Keith. Right. So good evening to all, and thanks for the kind introduction. I am Biju George, and I'll be discussing with you on the topic addressing the challenges in the integrity management of floating production storage and offloading facilities, the FPSOs. First of all, I'd like to thank Keith Lilly and the RINA London branch for inviting me for this lecture and for coordinating the arrangements. This presentation will provide insights into some of the main challenges encountered in the integrity management of FPSOs and the new tools, practices, and technology that could be employed across a diverse FPSO fleet, potentially improving the integrity management and more effective performance that aligns with the culture of the offshore oil and gas industry. The discussion agenda in this session comprises of an introduction, an overview of the integrity management of FPSOs, the inspection plan development aspects, the inspection execution challenges, the anomaly management criteria, and the future trends in integrity management, and a summary at the end of the presentation. On a broader way, the climate change is becoming more rapid and widespread with irreversible consequences. Scientific evidences indicate if there is inaction towards climate change risks, the environmental challenges and the disasters feedback loops are predicted to push ecosystems beyond the tipping points. And at that stage, all efforts toward decarbonization will be rendered ineffective. In this context, I have a dream whereby the integrity management activities of FPSOs are carried out by minimizing the number of working at heights, the number of confined space entries, minimizing the number of working underwater, the minimizing transfer of aquatic species, invasive aquatic species, minimizing emissions of greenhouse gases, and to limit the global warming to well below 2 degrees Celsius and pursue efforts to limit it to 1.5 degrees Celsius, the IMO UN targets, to avoid the dangerous climate change and to maximize the use of digitalization and artificial intelligence. I believe you all share the same mission as I have. The global FPSO fleet is quite diverse. FPSOs of all sizes, ages, designs, and arrangements are in operation. And today, over 270 vessels are deployed worldwide as FPSOs. The integrity management challenges vary widely across the global fleet of FPSOs. With many assets well over 15 years since the key laying dates, the integrity and maintenance requires a large portion of the available resources. This commonly occurs when the field is in its later stages and operating margins are at the slimmest. Alternatively, the newer FPSOs are some of the largest ever built and are equipped with most modern digital condition monitoring and maintenance systems. While the requirements of these units are similar, the challenges faced are quite different. The integrity management of FPSOs could be categorized into the wells integrity that comprises of the downhole equipment, drilling riser systems and associated systems, the subsea integrity that comprises of the subsea equipment, the flow lines, flexible risers, control systems and associated equipments, the FPSO hull and marine systems that comprise of the FPSO hull structures and marine piping systems and the associated equipments, the FPSO moorings that comprise the suction pile, the chains, any polyester ropes, the mooring jewelry, chain stoppers, and associated systems. Then the FPSO topside structures comprising of the structural modules, the pipe racks, the local equipment rooms, the workshops, laydown areas, and so on. Then comes the pressure systems, the FPSO pressure systems comprising of the piping systems, the pressure vessels, heat exchangers, and associated equipments. Each one of these categories will be a topic on its own for separate discussions. Today, I'll be discussing with you on the FPSO hull and marine systems, which comes under the classification of structural integrity management strategies. This would provide overview on typical integrity management strategies followed on the FPSOs. The starting point of integrity management is the class rules and the industry guidance, which includes the applicable industry recommendations such as the API, the ISO, and the other regulatory requirements such as the IMO MOD code, the SOLAS, the MARPOL, the class and flag state requirements. The integrity management involves the inspection plan development, the inspection execution, the anomaly management, and the fitness for service assessments. Opportunities to support the FPSO integrity management can be adopted from several different areas. These include the procedural improvements, the application of new technologies, design improvements, and the utilization of digital solutions. Let's look into the inspection plan development. The structural integrity management program starts with a class rules-based foundation. The traditional inspection regimes use inspections on a calendar basis to verify the integrity of an asset. A key difference in the operation of FPSOs being that, contrary to the regular dry docking intervals of marine vessels of every 2.5 years, FPSOs often remain on station for the entire service life. Being stationary, FPSOs are subject to a more uniform parcel offloading pattern and site-specific environmental conditions that make the structural load aspects more predictable. This creates the opportunity to consider a different inspection regime from that of sailing ships. The RBI, the risk-based inspection, provides the alternate means to develop an asset-specific in-service inspection plan versus the class rules-based or the calendar-based inspection regimes. The RBI program uses more asset-specific sources of information in the initial development, building a customized set of inspection requirements that take into account the asset characteristics as well as other dependencies such as the environmental conditions, the degradation mechanisms, and the other structural properties. The RBI also takes into consideration the design features, the operating conditions, deterioration mechanisms, and the consequences of not doing the inspections. The RBI utilizes a risk assessment and management process to develop and manage a forward-looking inspection plan that direct inspections towards the areas of highest risk. It focuses on failure modes initiated by material deterioration or degradation mechanisms, where risk can be effectively addressed through inspection of the equipment and structures. By optimizing the inspection regime using risk-based techniques, opportunities may also be identified to minimize not only the asset risk, but also the safety risk to personnel performing the inspections. This is a proven dynamic asset integrity management method that uses risk techniques to prioritize the inspection activities, identify and understand the risk drivers, and as a consequence, develop and implement effective risk mitigation strategies. This specifies which components to inspect, identifies the degradation mechanisms, the components that are affected by these mechanisms, the appropriate inspection method for each particular type of scopes, and defines the frequency of the inspections. The development of the RBI plan involves the data gathering phase, the component grouping phase, the baselining and fitness for service assessments, design analysis that include the global and local strength and fatigue analysis, selection of components for structural reliability analysis, and the determination of target reliability level, and the fatigue and strength reliability analysis. Also involves qualitative risk assessment to identify critical elements and other factors that are not covered by the reliability analysis. Thereafter comes the RBI plan development phase that defines the inspection and the monitoring requirements. The component grouping phase delineates the components within the asset hierarchy into manageable logical groupings or inspectable units, with an understanding of the applicable degradation mechanisms driving the scope of inspection within the unit. The FPSO hull structures, the mooring systems, marine systems, riser systems, and the topside modules consist of many components, and each has a role and function in the overall integrity of the asset. Understanding the complex interactions and dependencies of these elements will determine the efficacy of the program. This boils down to a question of damage mechanisms and the correlation of these mechanisms across a grouping of structural components, if that correlation exists at all. In other words, what are the prevalent damage mechanisms? What is the best approach to inspect them? And what to do when anomalies are discovered for those damage mechanisms? The development of the RBI plan involves risk assessment and risk-based prioritization. A typical 4x4 risk matrix is shown here. The consequences of the risk event comes in the x-axis and the likelihood of having a risk event in the y-axis. It is noted that the risk assessment for the prioritization step will be limited to the scenarios resulting from the deterioration mechanisms of the components within the scope of the analysis, and which can be detected by inspection, but also further informed by the asset unique structural features. One key factor in defining the inspection frequency is estimating the likelihood of an undesirable condition occurring based on the component's current condition and degradation rate. The corrosion rates of FPSO structures depends on the effectiveness of the cathodic protections. In the case of cargo tanks, the cargo composition, the content in any space, the content composition, the inert gas properties, the temperature of the contents, the maintenance activities on the structures, and so on. The corrosion rate varies depending on the function and location of the structural component. The published literature on material wastage from corrosion for various structural components have been indicated on the screen here. Each inspectable component should have its own inspection interval defined based on the component reaching a damage condition rather than the failure, but realizing that the worst cases within an inspectable unit may drive the overall inspection frequency of that unit. For the RBI plan management, these decisions are part of the managing the plan with time and are directly dependent on the age of the unit, the structural configuration, presence of anomalies, and so on. The comparison of fatigue, factor of safety, and the probabilities of failures for various structural components from various literature have been shown on this slide here. And now moving to the inspection execution phases. So generally the underwater external hull inspections up to 30-meter water depth are carried out by divers. However, there are safety implications associated with this activity, and hence ROVs are widely used for underwater cleaning and inspections. This short video footage shows the cleaning and inspections of the hull using ROV. Actually, I was having some other video earlier and it didn't work, so I just pick up something else here. Should be showing the, anyway, it's a hull inspections getting done by the ROV. That's just to give a flavor of what is the activities ongoing. So that's what intent of showing here. So there's a sea chest over there. So all the grills will be, everything will be cleaned by the ROV. Instead of divers, we normally use we are with ROV. Divers can use that. I can do that work. So give a flavor of those activities. So if I go to the next slide. Now moving into the internal hull inspections. One of the challenges of the internal hull inspection is the confined space entries. The confined space entry is a high risk activity. The confined spaces pose dangers because they are usually not designed to be areas where people work. These spaces often have poor ventilation, which allows hazardous atmospheres to quickly develop, especially if the space is small. The hazards are not always obvious and may change from one entry into the confined space to the next. The carry out inspections on board an FPSO with concurrent production operations is a major undertaking and requires detailed integrated planning and supporting good coordination of activities. Entering a confined space, including tanks, requires complete cleaning and gas freeing of the compartment. There should be provision for ventilation, lighting, and access. Also requires certification that the tank atmosphere is safe for entry, especially if residues remain in the tank. A high temperature atmosphere in the tank could be prevalent depending on the location of the space. It is to be noted the equipment and the consumable handlings on site are more challenging on the FPSO when compared with any trading tankers. The factors to be considered for the confined space entries includes the tank isolations, the operational impacts, the personal aspects, the structural strength and fatigue aspects, and the financial aspects, to name a few. The storage tanks to be inspected need to be positively isolated as per the operational standards and taken out of service. The tank system's positive isolation can be a challenge, making it difficult for storage tanks and related piping systems to meet the positive isolation standards. The challenge is more noticeable with FPSOs converted from conventional tankers with pump rooms and bottom piping as compared to the newer FPSOs fitted with submersible pumps. Also, a safe de-isolation of tanks and return to service is required on completion of activities similar to a trading tanker. The operational aspect side, the simultaneous operation CMOPS aspects need to be managed effectively. For example, in the case of void spaces with dehumidification systems in place, the opening the tank for inspection reintroduces a more corrosive environment. On the personal aspect side, the tank cleaning operations may expose personnel to safety hazards such as the normally occurring radioactive materials, mercury, and so on. The people on board, the POB constraints while carrying out inspections is in order to accommodate additional personnel such as the rope access teams, scaffolders, inspection engineers and technicians, painters, tank cleaners, class surveyors, rescue personnel, and so on. They all need to be factored in. The other drivers that impact the tank entry include the structural aspects, since emptying a tank can induce higher hull stresses and low cycle fatigue effects that may increase the likelihood of structural damage over the life of the asset. Additional challenges are also faced by the operator and may involve financial aspects, including the inspection budget, scheduling, logistical aspects, and so on. For inspection at heights and confined spaces, drones have now been widely used and have been shown to be able to provide a visual survey and UT gauging of structural components inside tanks, confined spaces, and topside structures. This short LiDAR and video footage indicates the visual and UT inspections of the cargo tanks using drones. So drones are doing the work, gauging and visual inspection inside the tanks at heights. Otherwise, it has to be done by personnel in rope access. Personnel has to do this work. Quite a lot of safety impacts because of it. The existing cutouts in longitudinal structure, girders and structures are generally enough to have the drones to move around. The inspections using ROV has been proven effective in existing ballast and void tanks of the FPSOs when the unit has clean ballast water and tanks with good coating conditions. Yeah, we'll run this short video showing the ballast tank inspections using ROV. Again, I was trying to show another footage, but it doesn't work earlier. So this is a ballast tank inspection with ROV. So tank is filled with water, and then the ROV is tethered ROV should be operating inside. So it can do the gaugings as well, visual and gaugings. But it will not work for a cargo tank. The cargo tanks it won't be clean enough. And also the operators doesn't want to fill the tank with water. So, but it will work for the ballast tanks. Again, the planning, the examination route, actually that we should be, route planning has to be done properly so that we can maneuver the ROV inside the cargo, inside the tank. I go to the next slide. All right. The tank designs are also an influencing factor in the structural integrity management. These drawings show the typical arrangement of double hull and single hull structures. To improve the efficiency of tank cleaning activities, actually the single hull tankers are very complex. As we can see, quite a lot of structural components inside, and whereas compared with a double hull tanker, double hull arrangement, the arrangement will be clean enough. There won't be much restrictions for doing the activities there. So the current complexity inside the single hull tanks makes them very difficult to clean. The stiffeners, piping, stringers, and hard to reach areas cause tank cleaning to be troublesome and near impossible to automate. Reducing the complexity of the tank design as well as increasing the size of the access openings will allow remote technologies such as crawlers and drones to be utilized for tank inspections. Also, another thought about the design enhancement for the crude oil washing of the cargo tanks and the sludge management. The stiffener profiles inside the tanks could be modified such that there won't be any sediment accumulation on those stiffeners, and that will facilitate the crude oil washing. Again, another point is about the tank sections can be preferably located at the center line of the tank. Alternatively, the consideration may be given to a suitable list within the acceptable hull girder strength and stability parameters to facilitate flow towards the tank suctions or the suctions in the tank sumps if allowed by the double hull construction. Larger sized limbo holes to be provided through the transverse and longitudinal frames so that it will allow efficient cargo drainage to the pump sections as well. And one point is that the MARPOL requirements for the cow systems require a minimum of 85% vertical and 90% horizontal surface coverage. The consideration for additional cow machines during the design phase by a thorough shadow analysis is recommended to maximize the coverage, especially in way of the bottom areas. It could be considered to provide crude oil pumping system arrangement to run the dedicated crude oil pump for crude oil washing activities during the offloading operations. Also, adequate means of positively isolating the cow machines serving one tank for the rest of the system be provided to enable maintenance of positive isolation for confined space entries. Another point is about the arrangement of the top sides should allow for the entire cow machine to be pulled and laid down in case of any to carry out the regular maintenance activities. And also the approved temporary lifting arrangement may also be considered as an alternative. Another option would be the cow machines that can be removed in sections would be employed. Let's look into the potential solutions for the new builds. The alternative designs for the new builds and the alternative materials for construction of FPSO oil tanks could be considered. That could help in reducing the amount of residue and corrosion. Currently, the FPSO cargo tanks are constructed with steel and paint coated, which is inexpensive and bears the required strength, but it is prone to corrosion and fatigue stresses over time. Some of these possible alternative materials include the use of sandwich plate systems, that is a concrete laminated with steel, or steel laminated with epoxy, or high strength plastics or other composite materials. Another proposal would be the adjustment and increase in the location of the cow nozzles, that they increase the number of cow nozzles and possible implementation of cow nozzles near the floor of the tank that could assist in cleaning the shadow areas of the tank, but would require redesign and modification of the piping of the cow system. Also, the cow nozzles are typically programmed for rotation speed, rotation degree, the washing time, the flow rate, and the quality of wash. As an alternative to programmable machines, non-programmable machines could be used that wash all areas, preventing from only washing the bottom of the tank and leading to build up on vertical and other spaces away from the bottom of the tank. So I recommend a non-programmable machine has got the benefits as well in that way. All right. Another point to consider is about the conducting repairs while operating. The executing FPSO structural repairs while operating is a situation all operators typically face during the life cycle of the FPSO, even under the most rigid asset integrity management regimes. To overcome some of the challenges already discussed, operators must find solutions that will produce the expected result while having expectations of safety of personnel, environment, and the asset, reduced impact to production, achieving effective results, and compliance with class and statutory requirements. Some of the best practices to be considered when facing the situation would be the front-end planning, reduce or eliminate the tank confined space entry, reduce manpower and time, improve the tank inspection quality, and increase the visibility for remote operations. So if I go into details of that, the front-end planning is one of the most important activities leading into a successful repair campaign. When planning for offshore work, it is strongly recommended to have a holistic approach to safety, including planning for evacuation or injured personnel, emergency response, and tank preparation for confined space entry. Develop detailed repair specifications that are suited for offshore execution, including the qualified welding procedures for water-backed welding if as needed. The safety is paramount, and reducing or eliminating the tank confined space entries can greatly decrease the risk to personnel engaged in the FPSO operations. Reducing the number of personnel needed to enter a tank for manual cleaning and inspection provides the greatest personal risk reduction to an FPSO operator. The cost of cleaning, including number of personnel on board, the time needed, and amount of waste for disposal could potentially be reduced as well. Another major benefit of improving the design of the FPSO crude oil tanks is the ability to reveal issues with structural components or coatings. This is very important with a prioritized RBI program. Also, reducing the amount of visual interference from internal tank structure and remaining residues would increase the visibility for remote inspections. With regard to the anomaly management criteria, the assessment of coating conditions in accordance with IAC's recommendation 87 is indicated here. The good, fair, poor grading of coating conditions, depending on the extent of coating breakdown and presence of corrosion scale, has been indicated on this table and the schematics here. Again, the good, fair, and poor grading of coating conditions, depending on the extent of coating breakdown and the presence of scale, has been indicated in the schematics in accordance with IAC's recommendation 87. Another point is about the pitting corrosions, pitting intensity and grading as per the DNV guidance has been indicated here. The pitting corrosion is a localized form of corrosion by which the cavities are produced in the plating. It is common within the cargo, slope, ospec, and water ballast tank platings and can be aggressive if caused due to bacterial corrosion. The DNV guidance shown could be applied to assess and grade the pitting intensity and the pitting depth. Based on the pitting intensity and depth, we can grade that and plan the remedial activities. All right, let's look into the digitalization in the integrity management activities. This has involved adopting techniques from other sectors like aerospace and automotive. For instance, life cycle management, natural language processing, multi-physics modeling, and simulations. Today, we are prepared to embrace the recent transformations to enable the FPSO sector to adopt a new level of technology that is more familiar to Silicon Valley. Technologies like digital twins, augmented reality, autonomous functions, and artificial intelligence are changing the integrity management activities and belong to a broader industry trends of digitalization, applied research, and clean energy transition, aided by various technologies that are prepared to transform the offshore sector. The IoT and big data are becoming one of those technologies that are being incorporated into the FPSO sector as the number of devices connected to the internet is increasing. The physical devices connected to internet, the so-called IoT devices, share a huge amount of data gathered from the sensors and can be analyzed in real time to derive conclusions that can help to make informed decisions for continuous improvements within operations. A recent research carried out by myself in this field has proposed a framework that comprises of artificial intelligence technique of the deep Q reinforcement learning, DQ and formulation, as a solution to multi-objective optimization problem for the maintenance activities of offshore assets. The details of this work are available online in the University of West London repository and also published in Elsevier Science Direct journals, the Applied Ocean Research and Ocean Engineering, over the past years, and recently at the proceedings of at the last week's World Maritime Technology Conference 2024. A bit of insights regarding this research work. The technical problem formulation, the multi-objective problem formulation has been shown here. The main deck of an FPSO has been modeled in this work. A 15-year-old hull with the principal dimensions of 360 meters, length between perpendiculars, molded breadth of 55 meters, and molded depth of 35 meters. Commercially available loading calculator has been employed to parametrically define the model. The decision variables considered in this work were the design features, operating conditions, deteriorations experienced, and the consequence of not doing the maintenance activities. The schematic representation of the multi-objective problem formulation, taking into account the personal resources with the application of greedy algorithm, has been shown in the figure on the right-hand side. The application of DQN to solve the formulator problem of the maintenance planning has been presented in this figure. The DQN problem statement has been defined as to carry out the activities that have minimal site constraints so as to get higher weighted sum of the completion times at short time as possible, which leads to higher resource utilizations. The goal was to achieve the best trade-off between the turnaround time of the activities and liquidating the risk to the asset's performance based on the completion of activities in the FPSO work management system. Again, I will not go into details, but anyway, I can summarize something on that. Okay, benchmarkings actually was carried out. Benchmarking performance evaluations of the models was carried out. And in the simulations of this shown here, the learning curves of the greedy, hybrid, and the DQN models with respect to the number of time steps taken to reach the destination and the rewards per time step has been shown. The variation of the average time steps per episode and the variation of the average rewards per time step for the hybrid and DQN models with respect to the greedy model has shown that the greedy and the hybrid models perform better than the hybrid and the DQN models perform better than the greedy model. And as they get trained, they perform better. The contributions of the work are that a novel work management framework has been proposed that comprises of the DQN formulation as a solution to the multi-objective optimization problem for maintenance activities of FPSOs. The framework enables carrying out activities that have minimal site constraints, considering the design features, operating conditions, deteriorations, consequences of not doing the activities, and the time required to complete the activities to get a higher weighted sum of the completion times as short as possible, whereby achieving the higher resource utilizations. It has been demonstrated that DQN has a potential to be employed to develop a dynamic work management system that adjusts the maintenance activities by achieving optimal path for carrying out the activities that liquidates the risk to the asset's performance, depending on the changes achieved on the asset condition based on the activities completed. This potentially maximize resource utilizations, enhance asset condition, and lead to a reduction in the emissions from the asset and would supplement the regulatory oversight requirements. This work demonstrates DeepQ reinforcement algorithm as a potential to achieve a best trade-off between the turnaround time of the activities and liquidating the risk to the risk by the completion of the activities. This leads to optimize the condition enhancement of the FPSO and improving the energy efficiency operational index. With that, I am summarizing this discussion. It is to be noted that opportunities exist to support the FPSO integrity management and could be embraced by procedural improvements, application of new technologies, design improvements, and usage of digital solutions. Also, technologies that digital twins, augmented reality, and autonomous functions and artificial intelligence are changing the offshore sector and belong to the broader industry trends of digitalization, applied research, and the clean energy transition, aided by the various technologies that are presented to transform the offshore sectors. I would like to conclude by reminding you all, each one of us have a role to play in encouraging others and guiding youngsters and everyone to set their efforts towards climate change problem and to embrace the digitalization and maximize utilization of artificial intelligence techniques to make contributions in enhancing the safety of personnel, environment, assets, and increasing the efficiency and enhance the, efficiency and to achieve the net zero emissions target set by the IMO at the earliest. Also, I like to remind that we need to keep in mind that collaboration between the various stakeholders would be key to success in this journey. Thank you all. Thanks for